Gears are simple, but also complicated. Sure, it's just a bunch of teeth around a wheel, but those teeth are special. Most follow a shape called an involute curve, which is basically what you get when you do this. Do it both ways and you get what you'd expect to see in a gear tooth. Now there are a lot of properties that make this shape the best for gear teeth as opposed to teeth, but I'll skip that for now because I'd just be regurgitating something you can read yourself. Anyway, we have this gear tooth shape, and to cut that we need, say it with me, a gear cutter, which is shaped like the gap between the teeth and removes everything going on in here. But there's a problem. Every different gear size has a slightly different involute shape. So in theory, a different cutter is needed for every possible gear. And that has the potential to be ludicrously expensive. Fortunately, in the world of engineering, everything is an approximation. So gear cutters are made for ranges of teeth because between these ranges, the tooth shapes are similar enough. Which leads me into the next problem. How on earth do I reproduce this special involute curve in metal? String and markers certainly aren't going to cut it. So I'm not going to make an involute at all, because once again, engineering. The only part of the involute I care about is the very beginning where the tooth is. And it turns out a plain old circle is really close to this shape. At least that's what it says right here. And in this shop, I can make circles like it's nobody's business. In fact, this book even includes a conversion chart so I know what size circles I need to make and how far apart they should be, so that I can produce a cutter that looks like this, so that I can cut my own gear cutters, so that I can cut my own gears. Oh yeah, and for those who have been following along in recent videos, this thing will finally be involved. One last thing. Gears have pitches just like screws. Coarse pitch, fine pitch. And I have it on good authority that I'll need a set of 0.75 module gear cutters. Or for the Imperial folks, that's a dimetral pitch of 33.867. This is the value I use in this chart to produce all the circle diameters and spacings. Now, if you're wondering how I'm doing these calculations so fast, it's because I've been really working on my mathematical muscles lately. That is with the help of our returning sponsor, Brilliant.org. Brilliant is an online platform that makes it easy to stay on top of your fitness. No, not that kind of fitness. Your mental fitness. Brilliant has thousands of lessons in subjects like math and science, data analytics, logic, and even programming. Which is great if you're getting into something new or just trying to remember something you forgot. But what's the point of just learning something if there's no outcome? Unless of course you enjoy being obnoxious at parties. What Brilliant really does is makes you a better problem solver. It not only builds your repertoire of knowledge across all sorts of fields, but it also rewires your brain to approach challenges with skill and confidence. Whether that's optimizing your to-do list, or figuring out the hardest way to make gears. There are lessons on that too, by the way. By making the lessons short and memorable, Brilliant lets you get started anywhere. Even if you only have a few minutes a day, which I know we all do, you can still squeeze in a lesson that keeps things moving. What I like most about Brilliant though is how interactive the lessons are. I learn best by doing and being hands-on, so I love that every lesson is filled with sliders, dials, and knobs that let you manipulate and understand the principles. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/inheritance or click the link in my description. You'll also get 20% off an annual premium subscription. Anyway, that's enough math. Let's actually do something. We have to make gear cutters before we can make gear cutters, so let's start there. And I'm not expecting to need any gears more than 134 teeth, so I'll just make the 5 smaller cutters. First, I'll need some holders, which means I'll need some square bars to start with. With these all squared up and a band-aid on my owie, we can move on to the more important stuff. They need to hold these circular buttons, but they all need to be held at a 5-degree angle, so I'll get these set up to match, and mill an angled face on each. Of course, each of the buttons are a different size and spacing, so now I'll go through and drill and ream the various mounting holes. The space between is relieved a bit to make clearance. Then I can pop a dowel pin hole in the side that will make sense later. That's 5 button holders whipped up and ready for some buttons, so let's make those buttons. To start, this is really straightforward. First, turning the diameter to the exact dimension that approximates the involute curve, then whittling down a little mounting nubbins before parting it off. Then it's just rinse and repeat for all the other sizes. Now we have a pair of buttons for each size, but if the idea is that these are going to cut steel, they aren't going to do a whole lot. That's why I made these out of this bar of 10. Oh, sorry, I mean 01. Tool steel, that is. Which is easy enough to heat treat with a torch and a little canola oil. There are also a handful of bits from the Eureka cutter build I did recently that should have probably been hardened as well, so I'll throw these in the mix as well. And these are a little too brittle to actually use, so a couple hours in the tempering oven and we should be good to go. In the meantime, I'll work on a grinding fixture for these little guys. Nothing fancy, just a block with a 9-degree angled face and some holes for mounting those inserts. The idea is not only to sharpen the buttons, but also to add a little back rake on the edge so they'll cut better, hence the 9-degree angle, versus the 5-degree I put on the button holders. Okay, let's finish these buttons. I made the holes in my fixture block a press fit for the buttons, so I'll just tap a couple of them in place, which I'm realizing now I'll probably regret, then head over to the surface grinder, and the rest is pretty self-explanatory. Now to get these out of here. There we go. The rest of these are the same deal, but that's not to say it went without issue. Turns out they're still a little bit delicate. But I got most of them made, so while I have a replacement baking, I'll move forward with what I do have. The rake angle we just added to each button means there's a high point that we want to take advantage of for cutting. So when I tap these in place in their holders, I'm angling that high point towards the middle where all the cutting action is. Then after a little more grinding and very gentle hammering, I have all the gear cutters ready. Now I'm sure the inquisitive among you are curious how the different angles and such going on here are going to affect the approximation of the involute I'm going for. I am too, but not curious enough to double check all that math. So I'm going to take the book's word for it that it will all come out alright. Let's make the gear cutters. First I'll need some blanks cut from this hunkin' piece of 01 tool steel. A bit overqualified for what I need though, so first I'll lop it in half, then work on adding a hole through the middle, going deep enough for the several cutters that I'll need. What an absolute bore. On to the next part. That's the 5 blanks I'll need for the 5 cutters, plus 2 more because why not, but also because I did my math wrong. Now ideally I want all of these to have the same thickness so I have predictable dimensions, and that sounds like a perfect excuse to use the surface grinder again. Not only does it make quick work of getting everything to the same thickness, but also gives them a pretty professional looking finish. Alright, we've got some discs, let's add some teeth. This has the potential to be very cumbersome doing these one at a time, so instead I'll do them all at once. Which means, time for another side project. So basically what I've got here is an arbor that I can slide all my blanks onto. Then I can steal the nut from my Eureka tool to hold everything tight, and of course it's a good idea to now true up the outsides of all the discs to make them match. Okay, let's make those teeth. They're basically all going to look like this, and I'll need a way to rotate from tooth to tooth while I cut them. So let's get the rotary table set up. I'm starting flat, but I'll be standing this up here in a bit, so it's important that I actually square this up now to that bottom face. And I'm sure some of you might know what's next. Rather than search for some convoluted way to hold my arbor onto the table, I'll just take the whole damn chuck over and mount it with this adapter I made. Only trouble is that this setup is super tall. No room for my normal coaxial indicator to squeeze in here to center everything up. So I'll use the old-fashioned indicator method. Since the coax didn't fit, no chance a drill chuck will either, let alone a drill bit. So we'll skip the chuck altogether and mount everything right in a collet. Now I can just work my way around to drill the 12 holes. 12 holes that I never explained, but will make sense in a minute. Now I can stand this whole deal up, tram it in, and get to work with the slitting saw. First centering things up, then making some cuts that intersect into those holes I just drilled. A quick change in elevation for a second set of cuts, and all is revealed. I now have actual teeth, on 7 cutters mind you. With how long this is taking, I'm glad I made this arbor though. Doing these one at a time would have taken a freaking week. Alright, that's all my cutter blanks, and I'm about ready to form the actual gear tooth shapes on them. But it would be supremely silly to make them all, and then get confused which one is which. So I should probably label these. Just kidding, let's play with the pantograph. There are a few important pieces of information I need to add to each of these. That being the pitch, the pressure angle, which we didn't really talk about, but I'm using the standard 20 degrees, the trade number for the gear tooth ranges, and then the tooth ranges themselves. Not sure why both of these are needed honestly, but it seemed like a good idea to follow the other examples I saw online. I gotta say, I shouldn't care so much about simple lettering, but man, that looks good. Alright, let's wrap this up. Time to put our button cutters to work. I'll eventually use the slitting saw arbor to hold these cutters when I make actual gears, so it seems like the perfect thing to hold on to them now. I'll get this centered up in the forge awl, and now while I'm here I can't resist cleaning up the outside of this arbor. Some of you may remember how this happened, and well, I'm finally tired of being reminded of that. Much better. Now my number 6 blank goes in here, and the number 6 button cutter goes in the tool holder. I'll set the cutter height so that it's on center line with the lathe. Then the last thing is to get the button centered on the cutter blank. I don't have much to go by here, but I do know the exact width of the button holder, so I'll use that as my reference and scooch over half that amount. Then also get a 0 on the button tip. Now for the part I've been most curious about. Will my hardened 01 tool steel buttons actually cut my unhardened 01 tool steel blank? Only one way to find out. It's working. The cutters are actually working. I know it should work in theory, but it's an entirely other thing to see it work in person. This is going great. Okay, so that looked a whole lot worse than it actually was. The blank snagged on the cutter and yanked everything out of whack in the chuck, and somehow, nothing broke. Not the arbor, not the blank, and most surprisingly, not the button inserts. The copper softjaws got pretty mangled, which is easy enough to clean up with a file, but led me to the conclusion that I must have had things hanging a little too far out of the chuck. So I'm going to try this again by grabbing a lot closer to the end this time. And for good measure, I'm going to go even slower. This feels and sounds a lot better. And once I reach the correct depth, which is actually important and included in those button calculations from earlier, that's one gear cutter formed. The rest of the cutters are exactly the same deal, minus the heart-stopping crash, of course. And with the exception of the largest button cutter, which I had to grind down on the front and sides for clearance. Then just like that, I have all 5 gear cutters formed. But guess what? They're not done. They may be formed, but they aren't form relieved. What do I mean by that? If I were to try to use these cutters now, they aren't going to do anything but rub. I need to remove a little material behind each of the cutting edges of the teeth, a relief if you will, of the form. That's where this comes in. This beauty is the Eureka Gear Cutter Form Relieving Tool. I spent 2 entire videos making this sucker for exactly this operation, and I'm pretty excited to actually see it in action. My gear cutter goes on here, and then this mounts between the centers and the lathe. I want it to spin, but not like this, so a dowel pin in the side of the button holder takes care of that. Now you can see how the mechanism takes a spinning motion and makes more of a stepping motion. I demonstrated this in the last video with some paper, and we're going to do the same here. I just have to get the gear cutter lined up so that it stops with each click in one of the notches. Lock that down, get the button centered up, and we're on our way. Ha! It's actually working. It's a bit slow going, but you can clearly see the cut working its way closer and closer to each of the leading edges. The idea is I go right up to the point where all the blue is gone, then that's it. Well, sort of. I need to do the same for the outer edge as well, but that's easy enough with a squared cutter. That's the first cutter in the bag. And now that I know that this is all going to work, time for some show and tell.
All right, let's go.
We do need to call attention to the fact that you are wearing the Hoochie Daddy shorts and showing an absolutely scandalous amount of leg.
But who picked out the Hoochie Daddy shorts?
Well, I did, but the point is that you're wearing them and you're looking like a hooer. So you made this entire thing, you didn't buy it.
Everything I'm showing you, I've made. I just realized there's one thing I didn't make.
So you made this.
I made
and
this.
you did the little righty right with the pantograph.
So that was just a test.
Okay.
So that's a gear blank. I made 7 of those. I needed 5.
Gear blank. So
Gear cutter blank. I need to cut a involute shape on each of these teeth. And I can approximate that with some circles.
I don't believe that works. I'm sure it does work, but I don't believe it.
And so I've got 5 different sizes.
Are these the things you've been toasting in my oven for the last 3 days?
So like there's a bigger set. So I'm just using that curve in the middle. Each one's different size for different size gears.
Did you buy the pins?
I did buy the pins. That's the only thing I've bought. That and this and made this.
Cool. Oh my gosh, look at all the writing.
0.75 module gear cutter.
Okay.
A 20-degree pitch angle. Gear trade size number 3. Cutting teeth 35 to 54. That gear is not done. We're going to finish it together.
Okay, so you're going to finish it and I'm going to watch.
Yes, I'm not letting you run this one. I've already crashed this particular setup multiple times. We're going to slap that bad boy on there.
Okay.
And then we're going to lock it in place with a nut.
Did you make that last time? Or is that new?
No, because I made these gear cutters narrower than I...
See, I pay attention.
You do pay attention,
like,
see?
We didn't edit a part of a video where you made that little ring.
I'm glad you're humoring me because you pretty much know what's going on here.
No, I don't.
You don't?
No.
So I got a center here and a center here.
Okay.
And then this bad boy comes on in. Why is that locked? Crank it down for me, mama.
I can do that.
Easy.
That was like 6 levers to lock that thing in place. That seems excessive. Oh, is that what that little post is for?
Yes.
Oh
That
my
keeps things. This is what we're doing.
That's what we're cutting, but because of the way it's gonna put the curve on the. Oh my God, that's so cool.
I'm glad you find this as interesting as I don't.
Spoken like a man
So-
who's
so
absolutely sick of this project.
Yes. I need to get this lined up so that when it stops between teeth. One moderately sized crescent wrench and one the biggest I've ever used size crescent wrench. Be amazed. So I'm going to start cutting.
Okay.
And then I'll show you what happens, okay?
I hear it.
All right, we're touching.
Oh my God, I see it.
See it?
I was looking at the peak. I did. But you can see the blue is coming off the back.
That's exactly why I glued it, yeah. Behold.
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 Totally see it.
You can see it, right?
You can
the back
see,
of the
yeah.
tooth is
Like you,
deeper than there.
yeah, like you can follow that point to that point. You can see that they're not in the same.
Next step is to harden. You haven't seen this. This is playtime with Brandon.
We're mostly
Oh.
looking at the shorty shorts.
You know what's more impressive than my hoochie shorts?
Show me. Oh,
Oh,
that was a
weak.
very wimpy flame. There you go.
I need you over here because a phenomenon is going to happen. Things are starting to change color, aren't they?
Oh my!
Wait, wait, wait. This is called straw color.
Okay.
Keep watching, keep watching, keep watching.
Oh my god.
So I could stop there.
Okay.
This is a decorative treatment people do.
You know I love decorative treatments,
Yes.
but we have to go beyond the blue. Oh my gosh, it's getting lighter.
Yeah, it ends up going back to silver. That's why I was excited to show you.
I did not know that was going to happen.
The trouble is they call it cherry red. Cherries are different colors of red.
Ah, that's looking.
There we go. Just kind of hover your hand over it. That's hot, isn't
It's
it?
very hot.
I gotta be quick.
Okay.
And whoop. Oh god, that's hot. Oh, I didn't mean to drop that. That little heating I did there,
Yeah.
feel this. All that heat transmitted into that. I did the 4 parts earlier and I went to pick this up. I was like, oh my god, it is. I saw something shoot over here and I was like, did I just break a tooth off of it? Because this is really brittle right now.
You made that whole thing.
I made that whole damn thing. And I actually made 5 of them, which is why this project has taken so long. And the stupid thing is I only need 1 of them.
It's beautiful. It's amazing. It's incredible.
Thank you, my love. Thank you.
Okay, now that I've sufficiently impressed my wife, I can whip through the rest of these. Eureka-ing them, nearly melting them, and baking them. The only thing left to do is sharpen them, but at this point I'm more interested in making some test gears than doing this right, so I'll engage the cheat code. I also skipped the making of these gear blanks, which I'm sure you could figure out. Let's just make some gears. I gotta get a reference off the top to know the center line height, then just the smallest, minusculest touch on the side. Come in a very specific distance determined with some math, and then off we go. Okay, I'm slapping myself for making these 60 tooth, but even still, this is awesome. My very first set of gears, and a fitting culmination to this video. But not the culmination of the 2 months I've been working on all this. Oh no. There's one gear in particular that I still want to make, but it's a little more than just a gear. So until then, thanks for watching, and see you next time.